Welcome back to the deep dive. Today, we are focusing all our attention on April 26, 1986.
A date etched in history.
Definitely. The location, the Chernobyl nuclear power plant, specifically Unit 4, right beside the planned city of Pripyat.
And what happened there in the early hours was just seismic.
Yeah.
An explosion.
So catastrophic, it remains one of only 2 incidents ever rated level 7. That's the absolute maximum severity on the International Nuclear Event Scale.
Right. And, when you look at the sheer cost, Chernobyl is in a league of its own.
You mean financially?
Yeah, absolutely. Our sources confirm it's the single most expensive disaster in history.
Yeah.
Total estimated costs, containment, health fallout, economic impact, it's staggering. Over $700 billion US.
Wow. That number is hard to even grasp. It really challenged everything, didn't it? Political systems, science.
Fundamentally, it forced a reckoning.
So our mission today is to take this mountain of source material, the reports, the declassified files, scientific analyses, and try to piece together a clear narrative.
It's complex. How did a safety test?
A test designed specifically to improve safety.
Exactly. How did that lead to the reactor's complete destruction? The core meltdown.
And releasing, 400 times more radioactive material than Hiroshima and Nagasaki combined.
That's the estimate. It's almost unbelievable. It wasn't just one mistake, though. That's key.
Right. It was systemic.
Systemic flaws, yeah. Institutional denial. It's where engineering failure met, a kind of human arrogance, almost.
So to understand the catastrophe, we have to start at the beginning.
We have to, with the reactor itself, the RBMK design, and the dangers literally built into it.
Okay, let's get into this. Nuclear reactors make heat through fission, obviously. But the critical thing, even after shutdown, you still need cooling.
Absolutely critical. It's because of decay heat.
Explain that a bit. Decay heat.
So even when the main chain reaction stops, the leftover bits, the fission products, and the fuel, they're still radioactive. They keep decaying and releasing heat.
And that's significant?
Yeah. About 6% of the reactor's full thermal power. Now, 6% sounds small, maybe?
But in a massive reactor like Chernobyl's Unit 4...
Which was 3,200 megawatts thermal.
Yeah.
That 6% is more than enough energy to cause a core meltdown if your coolant stops flowing.
Catastrophic overheating.
And the RBMK needed a lot of coolant flow.
Just immense amounts. These RBMK 1000s were giants. They used ordinary water circulated by these huge electrically driven pumps.
How much water are we talking?
The documentation points to over 45 million liters per hour per reactor, just to keep things stable across all those individual fuel channels.
It's a staggering volume, which demands constant, reliable electricity.
Exactly. And that brings up the nightmare scenario. A station blackout. What happens if the grid goes down? How do you keep those vital pumps running?
Okay, so that's the safety gap they were worried about.
Precisely. In a total blackout, you've got backup diesel generators, but there's a lag.
How long?
Between 60 and 75 seconds for them to spool up to full power. And you needed that full power, 5.5 megawatts, just for one main pump.
A whole minute or more with potentially no cooling. That's the window of vulnerability. That minute where decay heat could just skyrocket temperatures.
And bridging that specific 60-second gap, that was the entire point of the test on April 26th.
That was the goal. It was purely theoretical at that stage. Could the turbine itself help? The idea was harnessing the turbine's rotational momentum, its inertia. As it spins down after the steam is cut off, could it generate enough leftover electricity?
Enough to power those main coolant pumps.
For at least 45 seconds. That was the target. To cover most of that diesel startup time.
Okay, makes sense in theory. But this wasn't the first time they'd tried this test.
No, far from it. The sources highlight a really troubling history here. Attempts in 82, 84, 85, they all failed.
Failed how? Like explosions?
No, not catastrophically back then. More technical glitches. Problems keeping the excitation voltage stable on the generator, or sometimes the recording equipment just didn't work properly.
But the fact that they kept trying.
It suggests a strong push from somewhere. Maybe pressure to just pick the box, show full safety compliance,
What's really alarming, though, is the note that the people writing the test procedure, they didn't even know how the RBMK behaved under these specific low-power conditions.
That's more than just a glitch. That's a systemic failure.
Yeah.
A huge institutional blind spot, almost denial.
And the whole environment. The sources mention a general lack of safety culture.
Yeah, and we see chilling proof of that with the emergency core cooling system, the ECCS.
The failsafe, what happened there?
It's designed to flood the core with water if a major pipe breaks. Standard procedure. But they manually disabled it for the test preparations. But then the test got delayed. The Kiev grid controller asked them to wait. And that ECCS system, it was left disabled for 11 hours.
11 hours running without that ultimate safety net.
Exactly.
Yeah.
Now, the ECCS being off didn't cause the explosion directly, but operating a reactor like that without its fundamental last line of defense for half a day, it's just blatant disregard for protocol, cutting the seatbelt before a risky maneuver.
Which brings us to the reactor's core design flaw, the thing that made the RBMK so uniquely dangerous.
The positive void coefficient, yeah.
Let's break that down. Why was this feature so hazardous?
Well, first, you need to understand why it was built that way. Unlike Western reactors using water for both cooling and moderating neutrons.
Moderating means slowing neutrons down for fission, right?
Correct. The RBMK was different. It was a dual-purpose design. Not just power, but historically, it was good for making weapons-grade plutonium.
Ah,
So it used graphite blocks as the main moderator, big stacks of it.
okay, graphite moderates. What about the water then?
In this setup, the water flowing through the fuel channels was primarily the coolant, but it also absorbed a significant number of neutrons.
So water took neutrons out of the reaction.
Yes, and here's the deadly quirk.
Yeah.
A positive void coefficient means that when that water coolant boils and turns into steam bubbles or voids,
Yeah.
that steam is much less effective at absorbing neutrons than the liquid water it replaced.
Oh, I see. So less water or more steam means fewer neutrons
Yeah.
get absorbed.
Leaving more neutrons free to cause more fission, which generates more heat.
Which causes more boiling, more steam.
Exactly. A positive feedback loop.
Hmm.
More boiling, more steam voids, higher reactivity, more heat, even more boiling.
A runaway train.
In certain situations, especially at low power, yes, it could accelerate catastrophically. Most modern reactors have a negative void collector. Boiling slows things down, a natural break. The RBMK, in certain modes, had a built-in accelerator pedal for when things started to go wrong.
So you have the dangerous design, the disabled safety systems,
And then
and
you
bad timing throws another wrench in the works.
the human element. That delay from the Kiev grid controller pushed the test off the experienced day shift,
And onto the night shift.
who had much less time to prepare for this really delicate, complex experiment.
It was actually in the control room.
Key players. Anatoly Dyatlov, the deputy chief engineer. He was supervising, reportedly putting immense pressure on the crew to get the test done.
Okay.
Then Alexander Akimov, the unit shift supervisor, responsible for the reactor itself. And crucially, Leonid Toptunov, the senior reactor control engineer.
How experienced was he?
Barely. He was only 25 and had just 3 months of working independently on that console. Inexperience plus high pressure. The recipe for disaster.
And the first problem they hit wasn't instability, it was the power dropping like a stone.
Right. They were aiming for 700 to 1,000 megawatts thermal for the test. They got down to 720 milliW, which was fine.
But then...
It just plummeted,
Yeah.
unexpectedly, down to maybe 30 milliW thermal, or even less, practically shut down.
Why? What caused that?
Something called xenon poisoning.
Xenon, like the gas.
Yeah, xenon-135. It's a byproduct of fission, and it's really good at absorbing neutrons, kind of like control rods do. It poisons the reaction.
Okay.
Normally, at high power, the neutron flux is so intense it burns off this xenon as fast as it's created from decaying iodine-135. But when they lowered the power...
The neutron flux dropped too.
Exactly. So the xenon wasn't being burned off quickly enough. It built up rapidly, choking the reactor, soaking up all the neutrons.
So the reactor just died down.
Pretty much. And this is where the really bad decision started.
Under pressure to get the power back up for the test.
Immense pressure from Dyatlov. They decided to basically brute force it. Override the xenon poisoning by pulling out control rods, lots of them, manually removing them far beyond safe limits to flood the core with enough neutrons to overcome the xenon absorption and get the power level back up.
That sounds incredibly risky.
It was beyond risky. It was
Yeah.
reckless. By 12:39 a.m., they managed to nurse the power back up to about 160 millijoule.
Still way below the 700 milliW they needed for the test.
Way below. But the cost was stability. To get even that 160 millijoule, they had pulled out almost every single control rod. Out of 211, maybe only 6 or 8 effective rods were left in the core.
Wow.
Plus, to try and manage temperatures, they were running the main coolant pumps way too fast, excessively high flow rate.
What did that do?
It meant the water entering the core was already very close to boiling point. So you had almost no control rods left, and the coolant was primed to turn into steam at the slightest provocation. The reactor was hypersensitive to that void effect, a ticking time bomb.
And the worst part, they didn't even know how dangerous it was.
That's the damning institutional failure. The RBMK design lacked a crucial safety feature, real-time monitoring of the operational reactivity margin, the ORM.
The ORM.
Basically, a measure of how many effective control rods are inserted and how quickly the reactor could be shut down if needed. It tells you your safety margin.
And they didn't have that reading.
No real-time calculation available to them. They had absolutely no idea their ORM had dropped way below the mandatory minimum, which was equivalent to having at least 15 rods fully inserted. Regulations required an immediate shutdown if the ORM fell that low.
But they couldn't see it. They were flying blind.
Totally blind. On the very edge of criticality without a functioning speedometer or safety gauge.
And in that state, they started the test.
At 1.23 and 4 seconds a.m., they shut off the steam supply to the turbine. It started to coast down, just like the test plan intended.
But the power to the pumps?
Immediately started dropping as the turbine slowed, which slowed the water flow through the core.
Less water flow.
More steam. Those voids started forming rapidly. And that positive void coefficient, which had been sort of held in check by the massive water flow,
now it took over.
It started driving the reaction rate up.
Yeah.
Power began to climb.
They must have seen it on the control panel.
Oh, yes. They realized they were losing control. At 1.23 and 40 seconds, Akimov slammed the AZ-5 button. The emergency shutdown. Scram.
The last resort.
Witnesses said the control room was calm, though. Maybe they thought, okay, test failed, shut it down, believing the AZ-5 would work.
But it didn't.
It did the exact opposite. And this is where the design flaw becomes utterly lethal. Even if the reactor hadn't been unstable, the AZ-5 itself was fundamentally flawed.
Okay, this is the core of it, the control rods. Why did pushing the shutdown button trigger the explosion?
It's one of the most horrifying design flaws imaginable. The RBMK control rods weren't solid boron carbide, the stuff that absorbs neutrons.
No. What were they?
They had tips, about 1.3 meters long, made of graphite, the same stuff used as the moderator.
Graphite tips on the neutron-absorbing rods. Why?
It was meant to enhance the neutron economy when the rods were fully withdrawn, pushing water out of the channel. But when the rods were almost fully out, like they were that night, the space below the absorber part of the rod and the lower part of the core was filled with a column of water. Water, remember, absorbs neutrons.
Right, so when they hit AZ-5, the rods start moving down?
The graphite tip goes in first. It displaces that column of neutron-absorbing water below it.
And graphite moderates neutrons. It doesn't absorb them well.
Exactly. So for those first critical seconds of insertion, the graphite moving into the bottom of the core actually increased the neutron population and the reaction rate locally.
It momentarily boosted the power instead of shutting it down.
Precisely. A massive, localized power surge right at the bottom of the core. This was the positive scram effect.
Had anyone ever realized this could happen?
Tragically, yes. It had been observed and documented at another RBMK plant back in 1983. But that information, classified, never put into the operating procedures. The operators had no warning.
Unbelievable. So the power surge was immediate and huge.
Instantaneous. Seconds after the button push, the output rocketed.
Yeah.
It went way past 530 millilitothermal almost instantly. Some models suggest it might have spiked to 10 times the reactor's normal operating power before things physically broke apart.
What broke first?
The fuel rods themselves fractured from the thermal shock. The fuel channels ruptured violently,
leading to the first explosion.
A massive steam explosion. The coolant instantly flashed to high-pressure steam mixing with fragmented fuel. It blew the reactor vessel apart.
And the lid?
The 1,000-ton upper biological shield, they called it Elena, was ripped off and blasted straight up through the roof of the reactor building. Gone.
Taking all the cooling pipes with it.
Severing everything, guaranteeing the core was now exposed, open to the air.
And then the second explosion just seconds later.
Yeah, 2 or 3 seconds later. Even bigger, more powerful. Estimated maybe 225 tons of TNT equivalent.
What caused that one? Still steam.
That's debated. The consensus is likely further steam explosions, maybe hydrogen combustion. But this second blast did the final damage. It completely pulverized the core, ejected burning graphite blocks and fuel chunks hundreds of meters away.
Which ironically stopped the chain reaction.
By dispersing the fuel, yes, the nuclear reaction stopped. But it started a massive graphite fire, fueled by the superheated graphite hitting the oxygen in the air.
There are these accounts for people outside seeing strange lights.
Alexander Yurchenko's account is chilling. He was just outside Unit 4, saw this very beautiful, intense, laser-like beam of blue light shooting upwards from the destroyed reactor hall, flooding up into infinity.
What was that?
Ionized air glow. just a raw visual manifestation of the immense radiation and energy release. Physics made visible and terrifying.
You mentioned the cause of the second blast is debated. What's the alternative theory?
The nuclear fizzle hypothesis. It suggests the second blast wasn't just steam or hydrogen, but involved a very brief, uncontrolled nuclear chain reaction, a prompt criticality in a small part of the dispersed fuel.
Like a tiny nuclear bomb.
A very small, inefficient one, yes, a fizzle. The evidence cited is weirdly high. Xenon 135 levels, measured days later, hundreds of kilometers away in Chernobyl.
Why is that significant?
Xenon 135 decays really fast. Half-life is only about 8 hours. To detect it so far away so soon, proponents argue it must have been blasted high into the atmosphere very quickly, like in a nuclear event, rather than just drifting slowly from the fire plume. It's not the mainstream view, but it's out there.
Meanwhile, back at the plant, firefighters are rushing in.
Absolute heroes, but completely unaware of what they were facing. The first unit, led by Lieutenant Vladimir Pripyat, they just saw a fire at the power plant.
Their job was to put out the fire.
Exactly. Prevent it spreading to the adjacent Unit 3, which was still operating.
Yeah.
The big danger was the roof. It was covered in bitumen, which is basically asphalt. Highly flammable.
So they went up onto the roof of the turbine hall.
Straight into hell. They found chunks of graphite scattered everywhere, burning debris, intense heat.
And the radiation.
Unimaginable levels. They described feeling pins and needles on their skin, a metallic taste in their mouths. Classic signs of massive radiation exposure. They didn't know it was the reactor itself. One firefighter famously said, "We didn't know it was the reactor. Is it the reactor or not the reactor?" They were getting fatal doses in minutes.
Compounding this tragedy was the failure to even measure the radiation accurately at first.
Utter chaos and denial. The control room instruments were useless, off the scale. Most portable dosimeters they had were low range, only up to about 3.6 röntgens per hour. They maxed out instantly.
Were there any high-range detectors?
Yes, one capable of reading up to 1,000 R/second, a lethal dose, very quickly.
Right.
But it was either locked away, couldn't be found, or was buried in the debris. They couldn't get an accurate reading.
Which led Akimov, the shift supervisor,
To refuse to believe the reactor core was actually destroyed. He saw the damage, the graphite, but the available low readings contradicted it. He clung to the idea the reactor vessel was intact.
and sent his men.
Sent his crew members, totally unprotected, into highly radioactive areas to manually open water valves, trying to pump cooling water into what he thought was a damaged but intact core.
A fatal decision based on bad information.
Catastrophic. Those workers received lethal doses almost immediately. Akimov himself, Toptunov, many of the firefighters and plant workers who were there in those first hours. They died agonizing deaths from acute radiation syndrome, mostly within 3 weeks.
So the immediate horror of the explosion gives way to denial. Political denial from the Soviet Union.
A culture of secrecy that cost precious time. The explosion was 1:23 a.m. Saturday. The world didn't know, officially, until Monday, April 28th.
And it wasn't the Soviets who broke the news.
No, it was Sweden. Workers at the Forsmark nuclear power plant, over 1,000 kilometers away, set off radiation alarms just going into work. Their shoes were contaminated, Sweden demanded answers, and that forced Moscow's hand.
And Pripyat, the city built for the plant workers, 50,000 people living right next door.
They weren't evacuated for 36 hours. 36 agonizing hours, breathing contaminated air.
And when the evacuation finally happened,
It was under false pretenses. Beast out, told it was temporary. Just for 3 days, they said. Pack only essentials.
so people left everything.
Yeah.
Pets, photos, documents.
Everything, believing they'd be right back. The initial 10-kilometer evacuation zone quickly became 30 kilometers. Eventually, 135,000 people were permanently displaced.
And Moscow insisted on the May Day parade.
Incredible, isn't it? Issued a directive not to cancel the May Day celebrations in Kyiv, just downwind. Keep up the appearance of normality even as invisible poison rained down. Peak Soviet denial.
Once the scales sunk in, though, there was this immediate fear of something even worse.
A secondary steam explosion, yeah. The Nightmare Scenario 2.0.
Explain that.
They realized the reactor core debris had melted into this lava-like mascorium, they call it. A mix of fuel, concrete, sand, incredibly hot, maybe 1,200 degrees Celsius or more,
And it was melting downwards.
melting through the concrete reactor floor. And directly below that floor were huge pools of water, the bubble pools, part of the pressure suppression system. Thousands of tons of water.
If that molten corium hit the water.
Bang. A massive thermal explosion.
Yeah.
Like dropping molten metal into water. but on a radioactive, gigantic scale.
Yeah.
It could have ejected vastly more radioactive material, potentially destroyed the other reactors. Just unthinkable.
Which led to this incredibly dramatic, heroic moment.
The Chernobyl divers. 3 engineers, Alexei Nenonenko, Valery Bezpilov, and Boris Baranov. They volunteered.
Volunteer for what?
To go down into the flooded, pitch-black basement corridors beneath the reactor, wade through highly radioactive water, find the valves for the sluice gates, and open them to drain those bubbler pools.
Knowing the risk.
They were told it was almost certainly a suicide mission.
Yeah.
The radiation levels were astronomical. They went anyway, found the valves in the dark by feel, opened them, the pools drained.
Did they survive? Early reports said they died quickly.
That was misinformation, part of the mythology. Amazingly, they all survived. They received high doses, yes, suffered health problems later, but they lived for many years. Antonenko is reportedly still alive today. They were decorated as heroes decades later.
But was their sacrifice actually needed? I read later analysis suggested.
That's the tragic irony, potentially. Later probes found the corium had actually started dripping into the water before they drained it. But instead of a massive explosion,
What happened?
when the molten corium hit the water, it cooled rapidly, fragmenting into this porous, pumice-like ceramic material. Relatively stable, some of it even floated. So the giant steam explosion might not have happened anyway.
But they didn't know that. They acted based on the terrifying possibility.
Absolutely. Heroism based on the best, worst-case knowledge they had.
At the same time, they were worried about the ground under the reactor.
Yeah, contaminating the groundwater was a huge concern, that corium mass sinking deep into the earth.
What was the plan there? Freezing the ground.
That was the initial wild idea. Use oil drilling tech to inject liquid nitrogen, create a frozen barrier underneath. Quickly realized it was impractical.
That's dead.
They brought in miners, coal miners, subway builders from Moscow and Kiev. Their task, dig a tunnel 150 meters long directly underneath the reactor foundation.
Why the tunnel?
The original plan was to install a massive heat exchanger in it, a concrete pad cooled by pipes to solidify the ground and draw heat away if the corium kept melting down.
Did they build it?
They dug the tunnel, working in brutal heat and high radiation. But by the time it was ready, they realized the corium had cooled and stabilized enough on its own. The active cooling system wasn't needed.
To the tunnel.
They filled it with thousands of tons of concrete. Not for cooling, but for structural support. To shore up the foundation of the damaged reactor building, prevent it collapsing further.
Now the cleanup on top. Getting rid of the debris, especially on the roofs, that's where the robots came in.
Or rather, where they failed. They needed to clear about 100 tons of intensely radioactive debris fuel fragments, graphite chunks off the roofs around the reactor, particularly Unit 3's roof, to prepare for building the first shelter.
High-tech solution, right. Remote control robots.
They tried everything. Soviet moon rover chassis, German police robots, Japanese models, about 60 different machines. Sent them up, pushed the debris off.
How did that work out?
Terribly. The gamma radiation fields were just too intense, fried the electronics, cooked the batteries. Most of the robots failed very quickly. Even the heavily shielded ones.
Oh, so technology wasn't the answer there.
Not at all. Valery Legasov, a key scientist in the response, famously said, "We learned that robots are not the great remedy for everything. The machines couldn't handle it."
Which left? People?
The biorobots, human liquidators, mostly young military conscripts.
Doing the roof cleanup manually.
90% of it, yes. Shoveling highly radioactive graphite off the roof. 3,828 men did that specific job.
How could they possibly survive that?
Extremely short shifts. They'd run out, shovel maybe 1 or 2 loads, and run back. Maximum exposure time was 40 to 90 seconds. Even then, they absorbed huge doses, average of 25 rem each, for that roof work alone.
Just incredible bravery or perhaps ignorance of the true long-term risk?
A mix of both, probably. Duty, orders, maybe not fully grasping the invisible danger, but it got the job done at immense human cost.
And all this was to prepare for the sarcophagus.
The first containment structure, built incredibly fast, between June and November 1986. A monumental feat of engineering under impossible conditions.
What was its main purpose?
Stop the ongoing release of radioactive dust, shield the environment from the exposed core, and crucially protect the thousands of workers still operating the other Chernobyl reactors, especially Unit 3 next door. They work in crane cabins heavily shielded with lead.
But it was never meant to be permanent.
No, it was a temporary fix, designed for maybe 30 years max. It was rushed, built remotely, full of gaps, structurally unsound in the long run.
Which led to the massive structure we see there today.
The new Safe Confinement, the NSC. That gigantic arch, 105 meters high, 256 meters long, the largest movable land structure ever built.
When was that put in place?
Construction started around 2010, finished nearby, and then it was slid over the top of the old sarcophagus in Unit 4 between 2016 and 2018. An incredible project.
And its purpose?
Designed to last 100 years. It seals off the site, contains the remaining radioactivity, and crucially, houses the remote-controlled cranes and equipment needed for the next phase. Slowly, carefully, dismantling the original sarcophagus and the reactor debris underneath.
When is that cleanup supposed to finish?
The current schedule aims for completion around 2065, a century after the accident.
Let's talk about that long legacy. 400 times Hiroshima and Nagasaki. It's not just the amount, but the type of radioactive stuff released.
Right. Different isotopes behave differently. Their danger depends on volatility, how easily they spread, and their half-life, how long they stay radioactive.
What were the main culprits from Chernobyl?
3 big ones stand out. First, iodine-131, very volatile, spread easily, short half-life, only 8 days.
So the danger was intense, but brief.
Intense initial danger, yes. Got into the air, onto grass, cows ate the grass, people drank the milk. It concentrates in the thyroid gland, responsible for a lot of the initial radiation dose and, crucially, the later thyroid cancers.
Okay, what else? After the iodine decayed?
Then you worry about the long-haul isotopes. Cesium-137 is key, half-life of 30 years. Released as an aerosol, fine particles that drifted far and wide settled into the soil.
And it stays dangerous for decades.
Yeah, it gets into the food chain, mimics potassium in the body, can accumulate in muscles, including the heart. It's a major reason large areas are still uninhabitable.
And the third one?
Strontium-90. Half-life about 29 years. Chemically, it behaves like calcium.
So it goes to bones.
Exactly.
Yeah.
Accumulates in bones, irradiates the bone marrow, another long-term hazard.
And the spread wasn't uniform, was it? It depended heavily on weather.
Totally. Wind patterns, rain. That determined where the worst fallout landed. About 100,000 square kilometers were significantly contaminated across Ukraine, Belarus, and Russia.
But it went much further.
Oh, yes. Irregular patches, hot spots appeared all over Europe. Heavy rain washed contaminants out of the clouds, especially over mountains. The Alps, Welsh Mountains, Scottish Highlands, Norway. Some sheep farming restrictions still exist today because of Chernobyl cesium in the soil.
And the Soviets even tried to control the weather.
There's documented evidence of the Soviet Air Force seeding clouds, deliberately causing rain over parts of Belarus.
Why?
To try and wash the radioactive particles out of the air before the clouds reach major cities like Moscow. It worked, in a way, but it meant incredibly contaminated, heavy black rain fell on towns like Gomel in Belarus instead, just shifting the disaster.
Let's turn to the human health impact. We know about the immediate deaths.
30 confirmed direct deaths within the first few months. 2 from the explosions, 28 from acute radiation syndrome, ARS, among the first responders and plant staff. A handful more ARS-related deaths occurred over the next year or so.
But the long-term effects, especially cancer, that's always been controversial.
Highly controversial and hard to pin down definitively outside of one clear link.
Which is?
Thyroid cancer, especially in those who were children or adolescents in 1986, living in the most contaminated areas. That iodine-131 explosion.
How many cases?
By 2005, international studies confirmed over 6,000 cases in Belarus, Ukraine, and Russia that were attributable to Chernobyl radiation. Fortunately, thyroid cancer is usually very treatable if caught early.
How many died from it?
Sadly, about 15 deaths were recorded from those thousands of cases by the mid-2000s. A tragedy, but the overall mortality rate was low, thanks to treatment.
What about other cancers? Leukemia, solid tumors.
That's where it gets much murkier. Studies have generally not found statistically significant increases in leukemia or other cancers in the wider population that can be definitively linked only to Chernobyl radiation, outside of potentially higher risks among the liquidators who received the largest doses. But it's complex, hard to separate from other factors.
But the health impact wasn't just physical radiation effects. There was immense psychological damage.
Massive. Radiophobia. The fear of radiation itself caused widespread anxiety, stress, psychosomatic illnesses. People were terrified, often fueled by sensational media or lack of clear information.
And this fear had real consequences.
Devastating ones. Studies estimate that perhaps 100,000 to 200,000 elective abortions occurred across Europe in the months after Chernobyl.
Abortions performed because of fear of radiation damage to the fetus.
Exactly. Even in places where the actual radiation dose received was negligible from a medical standpoint. In Greece alone, an estimated 2,500 excess abortions were attributed solely to Chernobyl fears. Researchers concluded this was a tragic, unjustified consequence driven by panic, not medical necessity.
Let's look at the environment. The exclusion zone. 2,600 square kilometers. What happened there?
Immediately downwind, disaster. About 4 square kilometers of pine forest died quickly. The needles turned reddish-brown, became known as the Red Forest. It was eventually bulldozed and buried.
Water contamination, too.
A major worry, especially the Pripyat River feeding into the Dnieper reservoir system, which supplies water to Kiev. They built huge underwater dikes, silt traps, even a massive underground clay wall 30 meters deep to try and stop contaminants leaching into the groundwater.
But paradoxically, the zone today is thriving.
In terms of wildlife, yes. It's the ultimate irony. With humans gone, the lack of competition has turned the exclusion zone into a massive, accidental nature reserve. Wolves, wild boar, elk, lynx, Przalski's horses reintroduced. Populations are booming. Nature is resilient when people leave.
But the contamination is still there. You mentioned wild boar in Germany.
Yeah, it's a weird anomaly. Wild boar in some parts of Germany still test above the legal limit for cesium-137 consumption. For decades, everyone assumed it was all Chernobyl fallout.
That's not.
Recent studies analyzing isotope ratios, specifically cesium-135 versus cesium-137, found that in many German bores, a significant chunk of the contamination actually matches the signature of atmospheric nuclear weapons testing from the 1950s and 60s.
Wow, so Cold War testing fallout is still cycling through the ecosystem.
Seems so. It gets locked in the soil, taken up by fungi like truffles, which boar love to eat. It shows just how incredibly persistent this stuff is in the environment. A nuclear legacy lasting generations.
And we can't forget the people who went back. Mostly.
The self-settlers, mostly elderly people, maybe around 180 or so today, who illegally returned to their ancestral homes inside the zone. They refused to leave or came back despite the risks.
How do they survive?
Assistance farming, basically. Living off the land they know. It's a complex human story, defiance, attachment to home, maybe a different perception of risk, a testament to resilience of a sort.
Okay, back to the reactor site itself. Inside that huge new safe confinement arch, the danger isn't over, is it?
No, there's an ongoing scientific concern. Deep within the ruins, you still have tons of that corium fuel mass mixed with debris covered in radioactive dust.
And it's still potentially reactive.
Potentially. Remember, water slows neutrons down, making fission more likely? Well, rainwater still seeps into the structure as that water evaporates or levels change.
It changes the neutron environment.
Exactly. If water levels drop in certain areas where fuel debris is concentrated, it could theoretically allow neutron activity to increase, maybe even leading to self-sustaining fission reactions again. Not an explosion, but smoldering nuclear reactions.
Has this been detected?
There were worrying signs. Between 2017 and 2020, instruments detected neutron density doubling in one inaccessible subreactor room. It seemed to stabilize in 2021, but it's being watched very closely.
What's the risk if it starts up again?
The main fear is not a big power surge, but that sustained fission would generate heat, dry out the remaining material further, and potentially release more radioactive dust and aerosols inside the NSC, making the planned dismantling incredibly difficult and hazardous. It's a simmering threat.
Finally, the political impact. Chernobyl wasn't just a technical disaster.
It was a system-shattering event. Mikhail Gorbachev himself later said Chernobyl might have been the real cause of the collapse of the Soviet Union.
How so?
The sheer scale of the disaster, combined with the attempted cover-up and the obvious incompetence in managing it, completely eroded public trust in the government and the entire Soviet system. It forced Gorbachev's hand on his policy of glasnost openness.
Because they couldn't hide this.
They couldn't hide something impacting half of Europe. Glasnost, intended to strengthen the system through transparency, ended up exposing all its flaws and contradictions, accelerating its demise.
And declassified files later showed the flaws were known much earlier.
That was the ultimate indictment. KGB files released years later confirmed that scientists knew about the RBMK's key design flaws, the positive void coefficient, the graphite tips problem, as early as 1973.
13 years before the accident.
13 years. Reports went up the chain to the Central Committee, and they were essentially buried, classified, ignored in favor of meeting energy targets and maintaining political face. It was a systemic, top-down failure long before Dyatlov, Akimov, and Topchunov were in that control room. Catastrophe wasn't just possible, it was practically baked in.
And the economic cost still being felt today.
Hugely. Sources indicate Chernobyl still eats up something like 5 to 7% of Ukraine's entire national budget every single year. Belarus is heavily impacted too. The cleanup, healthcare, social support, it's a multi-generational burden.
It changed the world's view on nuclear power, too.
Absolutely. Triggered a massive global downturn in new reactor construction. Fueled anti-nuclear movements, especially in Europe. Germany's decision to phase out nuclear power has roots in Chernobyl. It starkly demonstrated the potential consequences when complex technology meets human fallibility and institutional secrecy. The cost of that secrecy was infinitely higher than the cost of openness would have been.
It really underscores the terrifying intersection of technology, human factors, and political systems.
You had the human errors pulling rods, disabling safety systems. You had the catastrophic technical flaws, the void coefficient, the graphite tips. And amplifying it all was the political failure, the culture of secrecy, the denial, a perfect storm on every level.
So the cleanup continues until 2065, potentially. The environmental impacts, like on Norwegian sheep farming, could last a century. And yet, there's still a chance of fission starting up again inside the containment.
It leaves you with a really profound question, doesn't it? In our increasingly complex, interconnected world, how do we make sure these hidden institutional flaws, these buried warnings, don't turn seemingly small errors into global crises that span generations? Chernobyl proved the biggest danger wasn't just the atom, it was the arrogance and secrecy surrounding it. What lesson from all this resonates most strongly with you? What's the enduring takeaway?